So before we get too far into this video, I want to draw your attention to two things. Number one, I shuffled the order. I apologize, which means the slide number referencing isn't going to work out perfectly. I screwed it up. I apologize. The other thing is, I already forgot. I don't know. So let's just continue. So with our E1 eliminations, what we're going to try and focus on is the aspect of them that makes them kind of complicated or difficult. And so what I'm going to focus on right here for our E1s is this mainly trans issue. And we're also going to address this Zaitsev statement on what that means. We're not going to directly talk about the complications of rearrangements and competing with SN1 because those, I'm going to argue, were already addressed when we talked about SN1. Okay, so let's go through and take a look at regiochemistry, your trans products. This is going to explode in complexity, so if you give me a second, I will try and erase stuff to simplify this down. But what we're talking about is that when we run the elimination, we have two possible products that could come out of it. We get the trans or the cis isomers. It does depend on what structure we're looking at, on what starting material we're working with, because it's possible the starting material we have isn't going to result in cis-trans isomers. But if there is the potential for cis-trans isomers, we need to be aware of that and wonder what's going on or evaluate what's going on with that when we look at our end results. So in the E1 elimination, if I was to say start with this starting material and I was to make a product of this, I'm going to be generating the double bond between where the leaving group leaves and where our hydrogen was removed. So if we just jump square straight away to the end result, we would have that pH for phenyl, so that's that benzene ring, not to be confused with phenol. Okay, we'd have our CH3 and our phenyl. Okay, so that would be our end result. Okay, yes, we skipped all the mechanistic steps and we jammed it all in there. But this does a couple things for us. Number one, it introduces that pH to give us an idea for that. Okay, the other thing we could introduce here is that CH3 could sometimes be referred to as Me for methyl. And then the last thing that we want to draw attention to is note that the angle of the bonds that I'm showing here are trying to reflect that 120 degree bond angles. Okay, you will notice that I am not drawing it in this fashion, pH, and methyl, because that bond angle doesn't exist. Okay, so be careful that when you go through and draw these things, you are trying to draw them as accurately as possible. Okay, so now back to our structure. We have formed this pi bond. Was there another way the pi bond could have formed? Couldn't it have also formed where the pHs were now on the opposite side of the forming pi bond? And so what we're really evaluating is the difference between a trans, because the phenyl is a higher priority than the methyl, versus a cis configuration. Okay, E1s allow for both, okay, or the potential for both. But because trans is more stable, we tend to see more trans. And we'll look at why we would see that here in a second. Okay, the first thing we need to address is why are both possible? And that's going to come back to our mechanism. So as our Cardi drawing is already trying to show, the first step is the removal of that leaving group. So the leaving group leaves, and we would have our pH. And if we were just being really kind of overzealous and not changing anything, we could show that as a wedge. Our CH3 would still be wedged, and we'd have that dashed phenyl, and then we'd have our hydrogen up here. If that bromine leaves, it would leave as Br minus. Okay, what is it leaving behind? Well, it's leaving a lack of electrons. So we would have a positive charge there, okay, which we've seen in the E1 elimination. What makes that now carbon interesting is that it is sp2 hybridized. Because it is sp2 hybridized, it is trigonal planar, and I can show all three bonds in the same plane. I don't need to specify wedges and dashes. yes, I can look at the molecule where it has wedges and dashes, but I need to be a little bit more careful about looking at it that way if I'm going to do so. Okay, so I want to modify this structure ever so slightly. And if you actually watch, it is a very slight modification. Okay, because where that methyl was aiming pretty much straight up. I'm going to be pulling it where I'm trying to show this coming out of the plane at you. So if we had a sheet of paper that represented, say, our hydrogen, carbon, and then this carbon, and I drew another sheet of paper, that sheet of paper, okay, would be perpendicular. We'd be looking one on the Y plane versus the X plane. So hopefully that makes sense when we're thinking about those orientations. Okay, why do that? Okay, well, the reason we're going to do that is that then allows us to see where the p orbital is located. The p orbital is now nice and easily drawn in that same plane as the hydrogen. Why does that become important? Okay, well, to do the elimination, the hydrogen has to be in that same plane so that those electrons can fold into that p orbital and form this overlap, okay, to form that pi bond. If, for instance, we rotated that structure, and again, we're trying to do this with pieces of paper on a flat object, but if we tried to rotate it where that plane was here, well, now where's the p orbital? Well, now the p orbital is coming in and out of the board at us. The hydrogen electrons are in a perpendicular system, or perpendicular plane, which means they don't overlap with the p orbital, which means we don't form the pi bond. Okay, so this orientation is of critical importance. Okay, so we did a slight modification. So we said we pulled the pH, we still kept it wedged, and that means our H is back here. Okay, so we could now go through and do the elimination as such and end with a potential product. Okay, and we're going to show this as our red arrow, and that red arrow is not going to disappear. So it'll stay there, but that's going to associate with this red arrow. At the end, we would get our product where we have our CH3 wedged coming at us, our pH going away, our pH coming at us, and we might go through and say, well, those are all trigonal planar. It's a bit dumb to draw it that way, so we could turn it so that it's all in the same plane, and that would be an excellent way to do it. And this is how we would typically see that answer written on a multiple choice. Okay, so there we go. We have that as a potential answer. The fun thing about, and everybody loves it when I call it fun, is that as soon as, it's not even as soon, if we take a look at this structure, that purple bond that's connecting these things, okay, is a sigma bond, which allows for free rotation. So I could have rotated that sigma bond. Okay, and for those people saying, well, wouldn't that have taken us back to this drawing where we don't get the overlap? Okay, well, we're not going to rotate it just 90 degrees. We're going to rotate it a full 180. Okay, so what happens if we rotate it a full 180? Man, how do I get my stuff? Okay, well, let's look at our drawing. If we rotate a full 180, we're going to leave the left-hand side of the molecule alone, so keep that wedged and dashed. There's our hydrogen. And if we do a full 180, that phenyl, instead of being aimed at you, is now going to be aimed away from you. The hydrogen is now aimed at us. Okay, so we're still maintaining that p orbital in the proper plane to do the reaction, and now we'll show it as blue. Our hydrogen could be removed to make that pi bond, and the end result that we would get after doing a slight permutation so that we could see it, notice the CH3 and the phenyl on the other side don't move, and we would end up with the cis product as opposed to the trans. Okay, so in an E1 elimination, because we have sigma bonds, we have that free rotation. Okay, the intermediate formed with that carbocation still allows for that free rotation, both of these pathways are available to the reaction and to the chemistry. Okay, deciding which one we get is going to be largely dependent on the interactions between these large groups. So how unstable is the cis? Okay, and what are we talking about those interactions? We're talking about this phenyl interacting with this phenyl in that intermediate. Well, I don't really see that interaction. Okay, well, if you don't see that interaction, awesome. That's exactly what I wanted you to say, because what we can do is take this carbon, our front carbon here, and I'm going to pull it out of the plane at you, and there it is. There's our hydrogen aimed up. The CH3 is aimed to the left. Our phenyl is aimed, CH3 would be to the left. Our phenyl is aimed to the back. If we go through and look at that back carbon, it's SP2 hybridized, which means we have a p orbital overlapping that plane of our hydrogen. And then we would have our phenyl over here and our hydrogen over here. The interaction that we're now generating here, that is a very high energy interaction. So what is the molecule going to likely do? It's likely going to cause those two to push away from each other, okay, which is going to cause a full rotation. That full rotation would potentially align us for the black Newman projection. So same idea, front carbon we'll call red. If we go through and draw that out, there's our front carbon. The CH3 is still to the left, pH is to the, I keep doing that. CH3 is to the right, the pH is to the L1, our left. Okay, there's our back carbon, there's that p orbital that's overlapping the hydrogen. Okay, and now where's my phenyl? My phenyl's over here, my hydrogen's over here. Okay, because that's a trigonal planar molecule. That conformation is a lower energy than the purple path, and so we would expect to see the trans come out of this in preference. Okay, Cardi has done a pretty good job, in my opinion, in trying to draw that all out, because it looks like a mess with how I've got it drawn, and this is what they're attempting to go through and show. If we do that rotation, here, he certainly isn't showing, because they're making it look like you're doing a rotation in both cases, but what we're talking about doing is trying to align so that we can get that elimination, and we either end with the trans product or the cis. Okay, and it's not easy to see that steric interaction unless you pull it out into a Newman projection, okay, which Cardi unfortunately didn't do for this one, but we'll see it when we look at the E2 in a little bit. Yeah, preview. Okay, I also attempted to go through and show it, except this time with the p orbitals, so that you can see that p orbital and that alignment of your hydrogen to allow your elimination and where you're getting those results. Okay, so we need to be aware of that for our elimination, and we need to be considering energy of our products when we go through to do this. Okay, why is the energy of the product such a big deal in the elimination? It's because these reactions are endothermic. When they become exothermic, we're a little bit more concerned about the energy of our reactants and less concerned about the energy of our products, because those products in an endothermic are now dictating your activation energy. Okay? So, since we're talking about stability, when we perform the elimination, we needed a hydrogen from a neighboring carbon. Okay? And so when we go through and looked at this, we're talking about, say, removing that hydrogen. Okay? And just bear with me because we didn't show stereochemistry, so don't stress about it. Or this hydrogen, which would have generated, say, the trans product. Okay? So cool, not a big deal. So are there other hydrogens? Well, yeah, there's hydrogens out here. What would the product be if I had removed that hydrogen? Okay, well, that now changes things. Instead of forming the double bond inside, I form the double bond outside. Okay, so there's another hydrogen that we could pull from. Okay, this is why it can be helpful to reference this as beta eliminations. You need to be looking at any beta position to your carbocation and decide, does that position have a hydrogen? If it does, that's a potential site for the elimination to occur. Okay, so we have to be aware of that. Note, all I've said is the potential site. Okay, To really go beyond that, to decide should all of those form, should only one of them form, what we really need to look at is what is the difference between those three products. Okay? Well, the difference between those three products is going to come down to energy. Okay? As we already addressed with the trans and the cis, the trans was more stable than the cis because we have these large groups as far away from each other as possible. Okay? So that makes the trans more likely than the cis. If we move to the terminal pi bond, well, haven't I gotten all the electrons as far away as possible? Wouldn't that make it even more stable? And it turns out, no, this is actually the least stable. Okay? And why? It's going to be the least stable because that pi bond is the most accessible. Because it is accessible, that means it can easily react. Okay? That ease of form of reactivity means it's higher in energy, which means it's less likely to form. Okay? And so we would expect the trans happening in this. Okay? Where this is ultimately coming from is trying to look at our Hammond postulates, and we can think about the difficulty for pi bonds to react and all that fun jazz. Okay? What we can really do is push this all the way into an energy diagram. And if we go through and look at an energy diagram for these, there's the formation of our intermediate, and now we're trying to decide A versus B. Well, B, we said, was lower in energy than A, and that's kind of our steric consideration. We got our electrons far away. Okay. Well, what happens with C? Okay. Well, C, the argument that I would go through and use with C is that those electrons, to react, just have to get by hydrogens. If we look at the electrons in B, it has to get by a carbon. Well, that carbon-carbon repulsion prevents B from reacting as much, which means B should be lower in energy than A. Okay, and I just noticed I had an issue here. Okay, which then means C should get placed even higher. So if we go through and run this reaction, we would see something along these lines. Okay? Because B is thermodynamically more stable, even if C happens to react and form, that reaction is easily reversible, whereas the formation of B is now unreversible or irreversible because it is a more stable product, and that ends up becoming my predominant or major product. Okay? This is all based off of looking at electrons and energies and stabilities of all of these fun things. Okay? That requires some pretty advanced knowledge. Okay? Unfortunately, when this was first discovered, we didn't have that advanced knowledge. What we had instead was that B forms, C did not, and A did not. Okay? So that must mean something is special about B. Okay? And what we decided was that B was the most substituted, okay, and therefore most stable. Okay? This becomes known as what is referenced as Zaitsev's. There's like a million different ways to spell out his name. Okay? You don't need to memorize this as Zaitsev. What you need to memorize is that you want the most stable product in an elimination. That's the biggest deal. However you decide to do that is entirely up to you. Okay, but you don't have to reference it as Zaitsev's. Okay, and because I get the added benefit of knowing what the very next thing is coming up here, we'll hear reference to this something known as your heat of hydration. The heat of hydration is how much energy is released to take, say, that pi bond and hydrate it. And by hydrate it, we mean, and this should be not hydrate, this should be hydrogenate. Okay? So the addition of hydrogen to add alkanes, what is that energy released for that? Okay, so if we're talking about the heat of hydrogenation, it's how much energy is released when I add hydrogen. If we move to the terminal one, that heat of hydrogenation is massive because it is higher in energy than our trans. So the heat of hydrogenation is really just another way of saying which one was more stable. The more stable your pi bond, the lower the heat of hydration. Same thing as heat of combustion, same concept at least. Okay? So all of this said, what this now references is this substitution patterns. Okay? And when we looked at trans, we're referencing our cis. Our trans and cis are our di-substituted. So the di-substituted have this potential of splitting into trans and cis, and because of how this is organized, we should probably write trans, then cis, and then our mono-substituted. Okay? So all we're trying to do is now reference this, which now brings in a new terminology, a substitution pattern for this. Okay? Well, what does it mean to be tetra-substituted? If we go through and look at that, there's 6 carbons there, not 4. Why are we calling it tetra-substituted? Because the pi bond, so where the alkene is, has 4 not hydrogen things connected. The tri-substituted, again, we look at where our alkene is, has 3 not hydrogen substitutions. Di-substituted has 2. Mono-substituted has 1. So what we're referencing is how many not carbons are, or how many not hydrogens are connected to your pi bond. And it's a connection to. I will very commonly get people telling me, for example, in this one, well, this one is di-substituted because there's 2 carbons. There will always be 2 carbons in an alkene when identified this way. That is not what we're referencing. We're referencing the things that are connected to the carbons of the alkene. Okay? So I just want to make sure we're extra clear on that. Make sure you're referencing that appropriately. Because otherwise you're going to be like, well, all alkenes are double substituted. They aren't. We're looking at the things connected to it. Okay? So the more substituted, the more stable. And we've got stepwise circling each of those substituents. Okay? If an elimination reaction gives us a choice between which of these we should make, the major product is going to be the one that is more substituted. This is what's known as Zaitsev's rule. Okay? Zaitsev knew nothing about energies of these particular substances. He just noted that when these reactions happened, we ended with the more substituted product. So we said the more substituted product is the one you get. Okay? We know more than that because we know energies. We know electrons. That's why we should be thinking about looking at these reactions based off of stabilities, not based off of some long dead Russian dude's observations about the world. Okay? Even if they were right. You'll notice there is an exception, Hoffman. We will see Hoffman eliminations pop up every so often. I don't know if, in fact, I know I'm not going to talk about that as a weird exception in this chapter. I might address it in chapter 9. Okay? So with that, we have our fundamental pieces for what products we would expect out of an E1 mechanism. So here we go. We've got a reaction. And in this case, I'm telling you it's E1. How do you know I'm telling you it's an E1 elimination? Subtle hint. When we look at the reactions, or really the mechanistic pieces that are shown, we see a carbocation. That's how we know it's an E1, because the 1 type is going to favor carbocations. Okay, so now the next question is, what would our final product be? Since we know this is an elimination, you need to be removing the hydrogen to make a pi bond. You've got a bunch of choices, figure it out. No, like pause the video and draw some products. Okay? And by some products, don't draw just the answer, draw all the possible answers that you can think of. So cool, hopefully you're now back because you've drawn those answers. If we go through and look at a potential answer here, go, ta-da, there we go, I did it. Okay, and what happened? I'm saying B came in and attacked. That is a phenomenal answer to a different question. Okay, what we just showed there was the substitution. Okay, this is not a substitution reaction. I asked you to do an elimination. So to do the elimination, that B is actually a B4 base, and we should remove a hydrogen. When we remove a hydrogen, the electrons holding that hydrogen on will now need to go into a bond, and the result we would get in that case would look something like that. I could have also had the base remove this hydrogen, and we would get what I'm going to call the green product. And we could have also had our base remove this hydrogen. Okay. Note, I even drew that hydrogen as far as humanly away as possible to try and get you to not react it. Okay. It is still connected to a carbon that is beta, because there's our alpha, there's a beta, beta, and beta. Okay, so in this case, that alpha carbon has 3 beta hydrogens that we could remove. So we get 3 possible eliminations. Of those 3, we would expect the red one, because that red one is what substitution? Tri-substituted. 1, 2, 3, 4. Okay. How many substitution is our green one? 1, 2, 3. And our blue one, 1, 2. Okay. So with that, we've got our complications done with our E1. And we can now move into our E2 with our big E2 summaries. We should remember that these all happen in one step. The big thing we want to be addressing here is, again, that I'm a little bit nervous because I can see the next slide, and it's not the next slide I thought it was, so we'll see what happens here in a second. But we've got those big summaries. It's all happening at once. If we were to look at an energy diagram for this, we again still have the potential for 3 possible results, because we could have removed hydrogen A, we could have removed hydrogen B, and don't stress about the stereochemistry on those, or hydrogen C. Okay, so we end up with 3 potential results again. How do we decide how to go through and look at this? Okay, well, it's again one, or not again, but it is one step, which means I'm going to move from reactant to product. Let's go ahead and take a look at A first. So that product A should be higher in energy than the reactant, because I'm looking at an endothermic reaction, the formation of a pi bond. It's in one step, so single hump. B is lower in energy than A because it's trans, so I'm going to put B down here. And C is higher in energy than all of them, and so we can put C up there. Okay. When we go through to run this elimination reaction, which of those is most likely to get us our product? Okay, well, which one has the smallest activation barrier? So in this case, B is our primary product. It's going to be very difficult to get A or C as potential products in the E2 elimination, just because of, or this particular E2 elimination, because B is going to form the fastest. Okay, there's nothing restricting the formation of B. Okay, that said, could something restrict the formation of B? Sure, why not? How about instead of there being a hydrogen at that blue position, it's now a methyl? Well, now there's not a hydrogen present to do the formation of B. Now which reaction is going to happen fastest? Well, now we should get A instead of C. Okay? For those people at home being like, but that's a sigma bond, can't you just rotate? That is a phenomenal question, and I really, really, really like it. And I'm hoping that with a few clicks here, we're actually going to encounter the slide that's going to discuss that. And hallelujah, there it is. We've got it. Okay, so let's go through and take a look at this. Okay, I'm going to go through and erase the bottom structure for the moment. And if we're going to look at an elimination, Here's our base. It comes in, removes the hydrogen, and at the same time our hydrogen comes in to form the pi bond and kicks out the leaving group. Okay. Note in this case, we are in the optimal alignment. This is the anti-periplanar alignment. Okay. This is a required alignment. It's a backside attack. The hydrogen has to be directly opposite that leaving bromine. Okay. So that would go through and we could produce our products. If we looked at where that pi bond would form, there's our pi. If we wanted to get particularly irritating and have to do some extra analysis, we are forming that pi bond with no option for rotation, which means we'd get something along these lines. If we cleaned that up and got rid of or acknowledged that this was a three-dimensional molecule, or sorry, a planar molecule, because those are all SP2, we'd show our double bond. Here's our CH3. Here's our phenyl. Now the other question, where does the remaining phenyl go? Because it sure looks like it's aimed upwards. Remember, it's not aimed upwards, it's aimed at you. The same direction as the methyl, which means if the methyl is being shown to the bottom, the phenyl needs to be shown to the bottom as well, and we would end with that product. Okay? Hopefully that makes sense. This would get us the trans alignment. Okay? Well, just like with the SN1, shouldn't we be allowed to do a rotation? Isn't that sigma bond in purple now allowed to rotate? Yes, it absolutely is. Okay, so to that end, let's go through and do that rotation. And I'm going to hold the left-hand side of the molecule static, and I'm going to rotate the right-hand side. And by doing that rotation, I'm going to align it so that the bromine is now aimed up. Goodness gracious. Oh, nope, I figured it out. pH, CH3. And now if we went through and did the elimination on this structure, wouldn't we end with the pi bond here, dash pH, CH3? For those of you being like, this seems awfully suspicious that you're driving so fast through this answer, you're right, it is. We'll address that in a second. Wouldn't this get me then the cis configuration? Right? Everybody see that and agree and be like, yes, that would totally get you the cis configuration. Yes, that is indeed cis. That is fantastic, except that elimination doesn't happen. Okay? What is wrong with the mechanism? All the arrows are shown from negative to positives. Leaving group is taking the electrons. I mean, that arrow looks a little sloppy, but you know, that's an arrow. Okay, that one's still an arrow. What's wrong with this? Okay, the what's wrong with it is literally written in bright red letters right above. To do the elimination, you must be anti-periplanar. The electrons coming from the hydrogen, this red, now red arrow, need to be anti or opposite the electrons of our leaving group. They are not in this orientation. Because they are not in that proper alignment, that means that arrow, or none of those arrows, are actually allowed to function. Well, if none of those mechanistic steps happen, I don't form that, and I don't form the cis. With this particular molecule, I can only get the trans. So the E2 is neat. Remember with the E1, we could say cis or trans, or technically cis and trans, but a larger favoring of the trans. With the E2, just like with the SN2, we only get one product, or have the potential to only get one product. And that's an interesting observation to make. So we have to be a little bit more careful when we run our eliminations to make sure that we're aligning in that anti-periplanar alignment. Again, our Newman projections, which I think will show up in a subsequent slide here, but if we pull that carbon forwards, there's our hydrogen, our CH3 to the right, our phenyl to the left, there's that hydrogen, our back carbon, our bromine is aimed down, there's the phenyl, there's the hydrogen in back. here's our anti-periplanar alignment. Okay, they have to be on opposite sides, just like our SN2. If we go through and look at the purple structure down below, and we do the same kind of thing, remember we didn't rotate the first atom, and we now look at the back, where's the bromine? The bromine is actually eclipsing everything else, which should be a giant red flag that we've got a problem, because to get, even align these things, to get that elimination, we have to rotate the molecule to be a peak, to be a transition state of a conformation. That doesn't exist. Okay? That means we can't run that elimination. Right? It doesn't happen. Okay? But what if I want the cis? Well, dang. What do I do now? Okay? Well, we've got another problem for you. Go through and solve this one and see what you come up with. See if you can get the cis product. Do whatever you got to do. Just do it. Okay, that means pause, and you should draw it. Did you unpause and wondering what's going on? Why is it so quiet? This is me attempting to get everybody to draw it. Okay, now we'll start. We're in the anti-alignment. Look, our leaving group aimed down and to the right, our hydrogen aimed up and to the left. We're in our alignment to do this. There's one phenyl dashed, there's the other phenyl dashed, wedge CH3. In this alignment, holy smokes, the pHs are now on the same side and we now have the cis. Didn't we just say we couldn't do the cis when we had this structure? Okay. You'll also notice that I suspiciously erased the previous compound. These two compounds are not identical. They're actually diastereomers of each other. And because they are diastereomers, we can end up with the cis-trans isomers forming in either one of these. Okay? So you need to be extra freaking careful when you look at your starting materials with elimination reactions, particularly with E2s, to make sure that you maintain the alignment of those groups, because otherwise you could make it become trans when it's supposed to be cis, or make it cis when it's supposed to become trans. We have to have that anti-periplanar alignment. The E2 will only get you one product, and it's the stereochemistry of that starting material that's going to dictate which product you get. Okay? This usually relies on needing to go into the Newman projections so that you could see these, so that you could do those individual eliminations. There's only one Newman projection that is going to allow the elimination, and that's that anti-elimination, that anti-alignment. Okay? Why is it not relevant for E1? Well, in the E1, what did we have? We formed a carbocation. So if I go through, remove the bromine on one of our drawings, let's not do it down there, I'll actually redraw it. If I remove the bromine, I get a hydrogen, a phenyl, and then I would have that p orbital, okay, on the front carbon. That p orbital is my carbocation. Why do I not need to worry about this at all when I'm looking at the E1? Because in the E1, that hydrogen that I'm removing could be removed in any of a variety of different locations. I could have the hydrogen come off where the hydrogen is oriented below the plane, so that it aligns with that p orbital, or I could have changed the alignment around so that the hydrogen was aimed above the plane, assuming I did that right, I think I did, such that we could get the elimination happening the other direction. Okay, so that we could get either the cis or trans products. It's that carbocation in the E1 that really kind of drives this that we've got to watch out for. Okay, so the E2, very commonly, you're getting stereospecific results, meaning you get one product coming out of this. Okay, usually, Okay, and why usually? Well, it is possible that there are two hydrogens that you could have eliminated, which means two of those possible, you get two potential hydrogens that could be removed. Which one would you form in preference? Well, you would still, just like the E1, form in preference the major product, your trans product, because that's going to result in a more stable Newman projection. Okay, so we can still get a mixture, okay, but it's going to be predominantly our more stable structure if we have those two options, okay, those two hydrogens that we can potentially remove. Okay, and so that's the key on when we're getting two products within E2, is that we have two beta hydrogens. Okay, with that, what we've really done is covered all of the basics of SN1, E1, E2 for all of Chapter 8. Okay, so if we consider our big overviews for Chapter 8, what you are being told is that the reaction is an SN1, an E1, an E2, or an SN2. Okay, with that extra information, you now have to predict the product based off of that initially given information. Okay, you can predict that product using curved arrows. You can predict that product because you've memorized what the product is going to be for that particular mechanism. I don't recommend that. I recommend you use curved arrows. Okay, the big thing that you're going to have to watch out for is that specified stereochemistry. If stereochemistry is not given to you, don't stress about it and just draw what you've got. Okay? But as soon as you see stereochemistry pop in, you need to be a little bit more careful about what you're drawing for your products and make sure that you're taking that into consideration, that when you draw your product, there might be products and you have to draw those multiple ones. The other thing to watch out is your mechanisms. Okay? If you see a carbocation, always think rearrangement. Always. Okay? When can you stop thinking about rearrangements? When you don't see a carbocation. Okay? And that's going to apply all the way through the end of second semester too. The instant you form a carbocation, a rearrangement should be screaming at you. Okay? Your acid-base steps, when you're drawing out a mechanism, if you're in a strongly basic environment, don't form acids. If you're in a strongly acidic environment, don't form bases. Okay? We want to try and keep our mechanism to be as real to the situation as possible. Okay? Intramolecular reactions, avoid them unless you're forced to do so. Okay? They're usually tricky and they're usually a bit rare. Okay? So when will we talk about intramolecular reactions? It's a good question. I thought they were already here, but I have a feeling I moved it to the very end of the slideshow because they can be tricky. So I wanted you to get some of the basics down first before we started throwing the curves of intramolecular. Just for the record, intramolecular means within. So given a starting material, how could it react inside itself in a substitution or in an elimination type fashion? Okay. With that, what I'll leave you with is the summary slide for our substitution and elimination that covers the big topics of what you're going to see in the next chapter. Substrate, leaving group, nucleophile or base, and solvent. And so what the next chapter is trying to get you to do is to look at those four categories and say, that is tertiary. That means this mechanism. Because what's going to happen in chapter 9 is instead of saying, do this reaction as an SN1, we're going to say, do this reaction, and you have to be able to decipher the information given within the reaction to be able to decide, should it go SN1? Should it go SN2? Should it do E1? Should it do E2? So you'll have to be thinking about what those pieces mean to be able to come to an interpretation. Okay, so we add a layer of difficulty on top of this. With that, I think that's enough for today, so I'm going to go ahead and stop.